So let us wait for few minutes. My name is Nitin Tomar. I am a PhD student in the Department of Mathematics at Indian Institute of Technology, Bombay. So this semester, our target is to see and learn, of course, the course Numerical Analysis. It is a rerun course. It is being taught by Professor S. Bhaskar from IIT Bombay itself, and I will be the TA for this NPTEL course. So let us wait for a few minutes and see if others join. Then we'll start. Yes. So, so when we say numerical analysis, the first thought that comes into the mind is doing analysis via some numerical methods, and that indeed is true. But at the very same time, one should note that what goes behind numerical analysis is the conceptual knowledge of your real analysis at the most. So, in the first lecture, we'll devote ourselves to some basic concepts of real analysis so that for the coming lectures there is no confusion. For example, in today's lecture, we will cover the convergence of a sequence, the continuous function, some basic preliminaries and results, and then we'll talk about the order of convergence. And with this, we'll see that these certain methods work in numerical analysis because the kind of concepts that goes behind them. Each and every method is not like has not fallen from the heaven. It has been there because a certain amount of conception analysis has gone behind them to construct such methods, and that is where the numerical analysis and the real analysis meet. If given a choice and someone asked me personally, I would rather say that these two subjects are not different. Numerical analysis can be thought as an application of real analysis. So that is why it becomes all the more important to have such a strong hold for real analysis, and that is what we intend to cover in the first lecture, some basic revision of real analysis. And yes, let us wait for a few more minutes and then we'll start. दीप तो मुझे हंसी मत दिला. Tim tana ta tim tana tim tim begone tu na chahe रूप कितना तेरे मन में है. बीच में एक बार शायद मैं तुझे थोड़ा तंग करूंगा चार्जर के लिए, तो जब मैं ऐसे से करूँ ना तो समझ जाइए मुझे चार्जर लगाना है। लगा दी। अरे इससे चार्ज हो जाएगा ना ये तो, है ना? इससे हो जाएगा ना चार्ज। मैं चेक कर रहा हूँ, एक मिनट। जरूरत होगी तभी लगाऊंगा। ओके, सो let us start. So we start with the convergence of a sequence. So first of all, what is a sequence? A sequence is an arrangement of number where we know what comes after another. More precisely, if one is to define a sequence in a mathematical manner, it is a function from the natural number to real number or any complex number. But in this course, we'll restrict ourselves to sequence of real number. So a sequence is basically a function from natural to real. So it looks like A1, A2, A3, A4, where AN is the general term and each AN belongs to the real number. So, as many of you must be knowing what do we mean by sequence and what do we mean by convergence of sequence, so let us cover it. So, when we say a sequence converges, what does it mean? It basically means as you keep on getting higher and higher in the chain of the sequence, in the chain of the numbers that are there in the arrangement, which we are calling sequence, all the elements in the sequence are getting closer and closer to one number, and that number is called its limit. Which means if I give you any distance, you can always find a stage in that sequence of real number such that from that stage onwards, the distance between that number, let's say capital L, and the members of the sequence is smaller than that fixed distance. Okay, so let us define it formally. So given a sequence, let's say an of real numbers, we say that the limit of the sequence exists, which we are denoting by capital L, if for every epsilon greater than 0 there exists a natural number n naught belongs to n such that mod an minus L is less than epsilon for every n greater than equal to n naught. So basically what we are saying here is the following. Let me just put it into writing. So let us suppose that we have a sequence A1, A2, A3, A4, so on and so forth. We say this sequence converges to L if what happens that given any, that is, that converges to L, what does it mean? It basically means that you take, is there someone joining? Let us see. Hello, am I audible?
Yes.
Okay. So, okay, let me just start again. So, numerical analysis. So, my name is Nitin, and I'm the TA of numerical analysis course. This course is taken by Professor S. Bhaskar. What we learn in the numerical analysis is the application of real analysis, which most of us have seen in our BSc course, or for that matter, any other functional master's level course. So, to understand numerical analysis better, it is always a good idea to start with the basic notions that we have learned in the real analysis, and that is precisely the aim of today's discussion. Today, what we'll see the convergence of sequence, the continuous function, some preliminaries and results, and one important theorem that we call as location of roots theorem. And we will see some applications of this via passing through Rolle's theorem, and then we'll discuss some questions. Okay, is that yeah. So? If you have any comment, or you know you can always unmute yourself and, and ask. Yeah. So when we say, so let us discuss the convergence of the sequence. So first of all, what is a sequence? A sequence is a function. Sequence by definition is a function, let's say f, whose domain is natural number and range is the real number or the complex number, depending on our range. But in this course, we'll mostly be sticking ourselves to the real number. So like, so one will goes to some f of 1, 2 will go to some f of 2, and so on and so forth. And hence, this way, one can always construct an arrangement of numbers where one knows what comes after another, or intuitively speaking, one knows one can arrange the numbers. So, this function is precisely denoted by a1, where a1 is the value of this function f at 1, then a2 defined in a similar way, a3, and so on and so forth, where each of this an is f of n for n belongs to natural number. Correct? Yes. So let me just rub it. Now, let us discuss convergence of a sequence, because this is one concept that will keep on coming again and again in this subject. So it's better to keep the tent on this subject and stay under it for a while. So convergence of a sequence. So can anyone tell me what do we mean by convergence of a sequence? Yes. This is more like a discussion session. So everyone is free to discuss. So it's a very basic question. What do we mean by convergence of sequence? Yes, exactly. Exactly. So, yes. This is precisely what we mean. So, convergence basically means after a certain stage, all these, like, okay, let us see what happens, step by step, so that there is no confusion. Because if we covers our basic right, if we covers our basics in a correct manner, then there will be no confusion. Let us, like we have this a1, a2, a3, a4. This is a sequence. We say this converges to a certain number, let's say L, which is in R. Okay, or maybe let us put it this way. Now what does it mean? That you fix any distance given any number which we denote by epsilon positive. I can always find a stage. One can always find a stage. That stage we denote by n nod, such that what happens. So a you have a1, a2, you keep on going, and then there will be a n naught, a n naught plus 1, correct, a n naught plus 2, so on and so forth. So what happens here, after this certain stage, all the values from here will have at most epsilon distance from L. That is, if we write it in a mathematical manner, what does distance mean? A n naught minus L. This is the distance, right? This will be less than epsilon. A n naught plus 1 minus L. This will also be less than epsilon. Then the next a n naught plus 2 minus L. This will also be less than epsilon, and so on and so forth. And if you combine all of this, so what does it basically mean? That a n minus L is less than epsilon for all n greater than equal to this n, which means after a certain stage you can stay epsilon unit close to your real number L. If that happens corresponding to every epsilon, if for every epsilon you are able to find such a stage, then we say our sequence converges. Okay. Now one thing I should ask here, what do you think? If I change my epsilon, will this change? It can so happen, right? If you change your epsilon, this stage can also change, and that is why we say this n naught, and yes, and that this is a very crucial thing. This n naught depends on the choice of epsilon. Yes. So let us see what does this mathematically mean. We say, so definition. Once we have the definition of convergence of sequence, life becomes easier. We say a sequence an converges to some L in R, because all of this is in R, if for any epsilon greater than 0, there exists there exists some number, let's say n naught in natural number, such that, or it's better to write this way, n naught bracket epsilon, just to show that this n naught depends on your choice of epsilon. So this n naught such that such that mod an minus l is less than epsilon for all n greater than equal to this n naught. Whenever we can find such a number l, then we'll say our sequence converges, and it converges to this capital L. Okay, so do we have any confusion here? Again I repeat, please free feel to discuss and comment, because this is a tutorial session. Okay, it's always good to have it's always good to have a certain discussion going on. It keeps the, just a minute. Yeah. Okay. Now, once we have the convergence, we'll see, so assuming that there is no doubt, the next important step in learning numerical analysis is the continuity of a function. Yes. Okay. I will again pose some question. Let A be a subset of R, and let F, we have a function. Now, please tell me, when do we say? We say F is continuous at a point A which belongs to A if, yes, please. Yes, and that is known as the, this yeah. Can you tell it in the, epsilon delta definition? Okay, that is some part of the definition, right? Hello, am I audible? Yes. No, you said, okay, let us write your definition. Fx minus f of a is less than epsilon, right? Is that so you said? Now, you see, I know the intention is correct, but I would like you to just see what you have said here. Now, the question, whenever, okay, you can mute yourself so that, so the question that can arise here, what is this epsilon? Okay, question is, what is this epsilon? Then question is, this is first question. Second is, where are these x coming from? Do you get my point? So whenever we try to put some definition forward, each and everything that appears in the definition should have a meaning and should be clear where they are coming from or where the context lies. So when you give me some estimate, this is an inequality, right? And this inequality involves some certain constraints. For example, what is this x? And what is this epsilon? So this does not make sense as the definition. Yes. So just hold on there. I give all of you 2 minutes. I give all of you 2 minutes and just see. Just try to write down the definition or recall the definition. Okay? Just take your time, take 2 minutes and try to see what is this epsilon and where are all these x coming from. I request all of you to please do this. So yes, is there anyone uh, who is eager to tell me what is this epsilon and where is this x coming from? Yes. Okay. Mm-hmm. Yes. Yes. So he's saying you start with any arbitrary epsilon, then corresponding to this epsilon, there exists some delta which is a function of epsilon greater than 0, such that such that mod of fx minus mod of fa is less than epsilon whenever whenever x minus a is less than delta. Correct? Yes. Now what does it signify? This is some mathematical expression, right? Now, intuitively, what does it say? See, all I'm wanting for all of us to have, discussion here, because that is how we all will learn. Lectures and every other thing you can see on NPTEL and they will be covered there. And whenever you have doubt, you can always come back here discussing that. But because it is a first lecture, so let us make sure all together that we are there on the basics, because down the road after 5 or 4 lectures this sequence convergence continuity they will be taken for granted. So it's better that we have a solid base here. Okay, that is why we are spending so much of our time here, because this is very important. So it says that whenever you have, so continuity basically means you look at the graph. Okay, let us draw some very nice graph. Let us assume that this is my graph. This is to you pick any a. Let's say this is my domain. My domain is, let's say this is my a. This is my capital A. This is the domain. Now, once I start with any epsilon, so this is my f of a, right? This is my f of a. So what does it say? That I fix any epsilon. I keep an arbitrary number epsilon in my mind. Then I should be able to find a delta such that whenever I am in the delta vicinity, whenever I am in the delta neighborhood of A, I should stay in the epsilon neighborhood of f of A. Right? Basically, what does it mean? The closeness to A will give me closeness to f of A. Correct? Is the idea clear what happens for the continuity part? Okay. Yeah. Okay. So this delta depends on epsilon. Now, if this so continuity is a local property, right? It depends on your choice of point. Am I correct? It can so happen given a function, there are points of continuity and there are points on which the function is not continuous. So continuity in that sense is a local phenomena. It's a phenomena which depends on the point. So we say a function is continuous on a domain or on a set capital A if for every point in capital A the function is continuous. Okay? Yes. And if it is not continuous at any point, then we say that the function is discontinuous at that point. And was what was done in the beginning, this is called the sequential criteria, as was mentioned by one of you in the beginning. That is called the sequential criteria. So we say a function is continuous at A continuous at A in A whenever, or let us put it this way, if xn converges to A, if for every xn in A, with xn converging to A, we have, what should we have? But f of xn converges to f of A. Now again, you see, you have to consider every sequence. Whenever we are learning the basics, we should emphasize when there is for every and when there is some. This is this is one of the most basic thing that like where one can get confused. What does it say? The sequential criteria say whenever you choose a sequence in the domain which converges to this point A, it should happen that f of xn should converge to f of A. Okay? And this is a very useful criteria, and this is only understandable because we know the convergence of sequence. Okay? Yeah. Now one important consequence or one important theorem that is related is the location of roots theorem. This is an application of intermediate value theorem. So let me just write the theorem. You have some compact interval a comma b, where a and b is in the real line, and let f from I to r be a continuous function. uh, just a minute, we have some. Yes, recording of the session will be there on the YouTube, whose link will be provided you by the NPTEL. Okay, does that answer your question, Atul? Okay. Again, I request all of you to please engage yourself in this discussion, because you see, we all are learning here. Okay, there is no foundation. Only I will speak or you will not speak. No, please let us discuss as freely as we can. Okay, and we start with a continuous function on I. Now we know what do we mean by continuous function. Now let us say if f of a times f of b is negative. Okay, then what should happen? It says that, okay, let me just picturize it for you. Okay, let us say that, this is my a, this is my b. Okay, and f is a continuous function in this stretch of interval. In this stretch of interval, f is a continuous function, and it says that f of a and f of b, whenever I take this product, it is negative. So what are the possible choices for f of a and f of b? Yes, yes, that is very good, but that is too far a conclusion now. The conclusion is correct, but let us go step by step. Okay, because we will not be discussing any proof here, otherwise it will take so much of our time, and we only have some limited time. But let us try to visualize whatever we can. So whenever we say the product of two number is negative, what does it mean? They must be of opposite sign, correct? If one number is positive, the other has to be negative, right? That is the only way the product can be negative. Okay, so let us assume that f of a is negative and f of b is positive. First case. So what does it mean? F of a will be somewhere here, right? F of a will be somewhere here, am I correct? As it is negative, somewhere, down on the negative y-axis. And f of b, it should be somewhere on the upper half, on the in the first quadrant, like this. Now you try to, like, picturize it. I want to draw a graph which goes from this point b of f, b comma f of b, and this point is a comma f of a. Now if you want to draw a continuous function, can you draw it without cutting or without having an intersection with the x-axis? I mean, if I am to, yeah, if I am to draw, it doesn't matter where I start. If I want to reach to this point continuously, which means without any break, then at least once I will intersect with the x-axis. Am I correct? It is very imaginative, it is very easy to see, because we are working with a continuous function. Again, I should highlight that we are working with a continuous function. Otherwise you can always draw discontinuous function like this, this value not taken, and you take this value. It does not cut x-axis, but is it a continuous function? No, right? So as long as I want a continuous function joining these 2 points, I should at least intersect x-axis once. It can so happen, it is intersecting at more than one point. But our claim is that at least once we should be able to intersect the x-axis, and that is happening because of the continuity part. Okay, is the conclusion clear to all of you? If you have any doubt, please ask. Should I destroy this picture? Okay, let me just delete it. Yeah. So then there exists at least, right? There exists at least one number, let's say C, which will belong to A comma B, such that what will happen? F of C is 0. Correct. Very good. F of C is 0. Which means C is the root of F. Yes. So, remark, this is a very common mathematical term. C is called a root of F. Okay. Now, if I let us discuss one example, and I would like all of you to work it out and then tell me. Okay. See, we have ample amount of time. We have 2 hours. Okay. So I'm not sparing you without doing, without making you write on your pen and without making you use your pen and paper. So let f of x, I consider this function x ex minus 2. Okay. Now, what I want to do, I want to give you an application of location of roots theorem, and that is used highly, that is used highly in numerical analysis, and this is called the bisection method. Why it is called the bisection method? We'll be very clear with it. Okay. So you take any interval of your choice. I am choosing 0 comma 1. Okay. First of all, is this a continuous function? What can you say about f? What is it domain of continuity? On on R, right? So this is, we know. Okay, so we are starting with a very, very nice function, right? So we should not have any problem. Continuous. And can you tell me why is it a continuous function on R? Can you tell me why is it a continuous function on R? Yes, yes. You know, sometimes I ask all these basic questions because there are students who are joining as a bachelor student. They are in their BSc program, they are in their undergraduate program. So it's very important that we discuss some of the basic here also. Okay, some of you might find it, too, what should I say, too time consuming maybe, but for students who are from undergraduate program, I think we should have certain discussion. We should not leave any stone unturned. So, as it is mentioned, this function is continuous on real number because it is a sum product and then, sum and product of certain continuous function. Correct? Yes. Now, tell me what is its sign on 0 and 1? On 0, it is positive or negative? What is f of 0? Very good. It is negative. It is minus 2. So it obtains minus sign here. And what about f of 1? It is e minus 2, correct? So this is it a positive number or a negative number? Positive, correct. So this is negative, and yes, yes, as e is greater than 2. Now, what does location of root theorem tells you? What does it tell you? Very good. There must, let us write it step by step. There must exist some c between 0 and 1 such that f of c is 0. Am I correct? Now, if I am to ask you, what should I do? Now, my aim is to find some root of this function, or at least be as close as to a certain root. I want to be in a very close neighborhood of a root of this function. So, what should be my next step? I should, first of all, I should stay in this neighborhood only, right? Because by location of root, it is guaranteed that there will be at least one root. Am I correct? It is it clear to all of you? Okay, who all are the contenders? Let me just point out. Hariom, is it clear to you? Okay. So for the time being, I know life is easy. I want to stay between 0 and 1. But 0 and 1, still there are infinitely many real number between that. Basic real analysis tells us that. So what do? I make a very clever approach. I cut this interval in half. Okay. So here you will have 1 by 2. Correct? Now, what should I do? I should check the sign of this function at 1 by 2, right? If it is, it will either be 0. If it is 0, then we are done. If f of half is 0, we are done, correct? There can only be three cases. F of half either can be negative, can be positive, or 0. Yes or no? If it is 0, then I am done. Half is the root. Remember, my aim is to find the root. So if f of half is 0, I am done. If f of half is, let's say, negative, correct? Then what can you say about the location of root? Let us say f of half is negative. So in which interval the root will lie? Half and 1. Very good. And let us say, but f of half is positive. Then what should we conclude from location of roots theorem? 0 and half. So in all the three possible ways, in all the three possible cases, I am able to draw some conclusion. Correct? Where should our root be? So let us check. Can anyone? Okay, you all of you tell me what is f of half. Is it positive? Is it negative? Please tell me. It is negative. I don't know, you please tell me. All of you, you come to a unanimous decision. Okay. It should. Mm-hmm. Yeah, the value is this, right? So this is negative. Let us say, if and only if root e by 2 is less than 2. Correct. Which is if and only if root is less than 4. Okay, which is obvious, right? Because e is less than, is close to 3, right? Yeah, so this conclusion is correct. Yeah, so this is negative, so f of half is negative. So I know this interval is a wastage, so I should stick to this interval, right? Half and 1, exactly. So it will say again by location of roots theorem, what will we have? Let's say this was c1, so there exists c2 between half to 1, such that such that f of c2 will be 0. Am I correct? Correct. Now can you see what should happen hereafter, and at every stage what we are doing? We are cutting the interval into half, right? Whatever interval we are starting, we are cutting the interval in half, and then again half, and then again half, and hope that we will finally reach the root of this function. Is what I'm trying to say here. At first stage, when nothing was no, we just took 0 and 1, we checked the sign. So at the end of step 1, we had this interval 0 comma 1. Okay, then we cut this interval in half on the basis of location of root theorem, and this was our step 2 at step 2. So again, I will repeat the process, and I can do this on and on. Am I correct? And what should be our expectation? I am not asking for a mathematical proof. Again, I am asking for your mathematical expectation. What do you think should happen? Hmm. Yes. Very good. Yes, exactly. Exactly. So the interval, okay, I'm writing something, you tell me if this makes sense. The interval gets half at the end of every step. Am I correct? At the end of every step. You see, if this length, let us draw a column here, length of interval. Length of interval. If this length was half, oh sorry, this length was 1. At the next stage, it should be half, right? And again, you will have 1 by 4, and you keep on doing this. Yes. And this is a convergent sequence. Am I correct? So at every stage, the first stage, I don't know, but the second stage it was A1 was half, right? Let us choose our A naught to be 1. Then we fix ourselves, the half. Then again you will get some, you know, A2 will be some number, and then this A3, correct? You can always construct such a sequence, right? And it should converge to No, this is not the length. This is not the length. One was A naught, A1 was half. Again, let us say you will again bisect it, right? Let us say that that number is 1 by 4 for the time being. Okay, then your A2 will be 1 by 4. So you keep on doing this. Basically, what I'm trying to say here, you keep on repeating this, you will get a sequence of number that will converge to your root. Correct? It should converge to your root because intervals are getting smaller and smaller and smaller. Does that make sense to all of you? Yeah. So this is called the bisection method, which you must have learned by now, right? Are you seeing the lectures? Because why is this called a bisection method? Because at every stage we are bisecting the length of the interval. Okay. So this is one application of location of roots theorem. Again, I want to repeat myself. Whenever we are trying to learn any sort of numerical analysis, it is it is very advisable to have a certain stronghold of your real analysis. For example, if one does not know location of roots theorem, one can always remember the technique of bisection method, because what are we doing? We are just cutting the interval into half, and then we are checking the values at the end point, right? It can be a very well a mechanical process. But if you know why is this method working, why does this method work? Come on, tell me please, why does this method work? Which theorem guarantees that this method will work? This is precisely the location of roots theorem. Correct? Yes. Because why we should go to the interval? Why should we consider the half of that interval whose endpoints have opposite sign? Because we know there will exist a root between that interval, and that is guaranteed by location of roots theorem. So as long as we have the conceptual knowledge, it is very easy to work with the algorithm of any method that is suggested in the numerical analysis course. So that is why we are spending so much time in learning these concepts. Okay, and again, it is a first lecture, so let us have some uniform time over every concept. Okay, so up until now, is everything clear? Okay, so please tell me if I'm going too fast, or or something that is off. Please tell me. Okay, now another important theorem in this sequence is the Rolle's theorem. Yeah. So Rolle's theorem kind of deals with the makes some similar conclusion, but for the derivative. Okay. Okay. Let me just write down the statement, not the statement, the hypothesis. Then we will discuss what should be the conclusion. Let us suppose f is a continuous function on a compact interval is a continuous function, and that the derivative exists at every point of a comma b. If f of a and f of b is 0, at end point The function takes the value f. Then what can you conclude? Again, we are not going to dwell ourselves into a certain proof of roles theorem, but let us try to be imaginative here and let us see what happens. Again, let us draw some graph. And okay, we don't need this, or maybe we need this. Yeah, this is my x-axis and y-axis, and let us suppose that this is my a and this is my b. And what are we saying here? That f is a continuous function in the compact interval, and in the open interval f is differentiable. So what do we mean by differentiability of a function? Can anyone quickly tell me? Yes, yes. Differentiability means, and what do can do you have certain geometric interpretation for that? For example, for continuity, if I were to explain a layman, for example, who is not a math student, let's just call like someone who does not know this concept. But if I were to explain him continuity, how will you explain it? Yes. So that is certain geometric imaginative interpretation you have there, right? Yes or no? But if I were to ask you, do you have a certain geometric interpretation in this possible way for differentiability? Do you have any? Does anyone? Yes. Don't be afraid of like anything. You just say whatever comes into your mind, and we will see what happens. Again, it's a discussion session, so we should be very more comfortable. Okay. So I request all of you to be free and discuss it here with me or with everyone else. Yes. Okay, let me give you two example, and you tell me what among them can be a differentiable function. These two are, let's say, graph of a function. Both of these are continuous, yes or no? But both of these are differentiable, not. See, this is one graph. Huh? This is one graph. This is first graph. This is second graph. Okay, which one is differentiable, first or second? Okay, who said this? Yeah. Why? Are these 2 points the where it is sharp, like this point and this point? Yes, yes. So the geometric interpretation of differentiability is the graph should not have any sharp turn. You know, sharpness should not be there. Otherwise, it will it will force the function to lose differentiability. Do you get my point? So the geometric, again, when I say geometric interpretation, it means in some sense you can think of continuous function as whose graphs can be drawn without lifting the pen from the paper. All of you agree with this? The same thing can be said for the differentiable functions, that the graph should not have any sudden turn. The graph should not have any sharp turn. Sharpness should not be there. Okay, for example, this function cannot be differentiable at so many points, but this will be differentiable. Okay, I hope this helps. Okay, yeah. V shape should not be there. Yes. Like, because you see why let's say we have this graph. Differentiability means you can always draw a tangent, right? So at this point, you will have two tangent. One will be this and one will be this. So which one will you choose? Okay. But here you will have only one tangent. Like this. So V shape should not be there. As soon as you have V shape, we call it sharp turn. As soon as you have a V shape, the differentiability at that point is lost. Yeah. So Rawls theorem says if you have a differentiable function, which means the function which does not have any V shape in the graph, and let us say at endpoints it takes the value 0, then what should be the conclusion? You have this 0, right? This is b comma f of b, this point, because it is 0, and this point is a comma f of a. Now again you have to reach a to b. How will you reach? Can I reach it without intersecting x-axis in between? I can always go like this, right? In between I am not intersecting x-axis, but that is not the point. Can I do it without making this u-shaped thing? Can I do this without making this u-shaped thing? Let us say we are going like this, and I have to come to like this, right, to reach to b. Try to think of it. You cannot come to b without making this u-shaped thing. Certain, u-shape, I'm referring them these two as u-shape. Downward u or upward u doesn't matter, they are shapes of u. I cannot do that, right? I cannot avoid this shape, can I? No, this is not given that these are the two routes. There can be other routes. Graph could be like this. Okay? It doesn't matter. What I'm asking you to think whether I can avoid this U shape from reaching A to B, from reaching these two coordinates. Can I do that? Not possible, right? Yes, yes, yes. Someone was saying something. Biswajit, you were saying something, right? Exactly. Yes, because differentiability will be lost. Exactly. That is why this differentiability comes into the picture. Okay. Now, what can you say about this point? Let us say this point is C. So, what will be this coordinate? This coordinate will be C comma f of C. Can anyone tell me a special property of this point? Derivative is 0, right? At this point, f prime C will be 0. Why? Because this is a point of minima, right? Everyone knows this. At the point of local maxima or minima, the derivative is 0. Yes. So, what I am going to write now, please tell me if that is correct or no. So, I am deleting all this stuff. So, what should be my conclusion? Then there exists, there exists at least one C between A comma B such that such that f dash c is equal to 0. Okay. Yeah. So is the conclusion clear? See, again and again, why I'm asking is the conclusion clear, because all these things can be thought of geometrically. You know, if we were to write a mathematical proof, that will require some rigorous, rigorous writing. But at the very least, can we say that the idea of the theorem is clear? Why should the desired conclusion hold is clear? Can I take that the desired conclusion is clear? Okay, let me repeat myself. Do all of us agree that the conclusion holds? Geometrically, at least. Yeah. Okay. Now, let us do some questions based on what we have learned, and which will be, like helpful in your learning of numerical analysis. Questions. So, question number one, you will tell me the solution, okay? We will take some time and then we'll think of the solution. Let L be a real number and let an be a sequence of real number. Now, if there exist some n positive and mu between 0 and 1, such that such that mod of this distance is less than equal to mu mod an minus 1 minus L for all n greater than equal to n, then show that limit an is L. Is the question clear? Can you prove this? Am I audible? Yes. So how do you think should we go through this question? What does it say basically? What is mod an minus L, and what is the entity on the left hand side of the inequality? What is this? This is the distance of L from an, right? And this is the distance of L from the previous term in the sequence. Now, what does it say? The distance is, each term has smaller distance than the previous one. Am I correct? You know, an minus L, this is the distance between an and L. Am I correct? And an minus 1 minus L, this is the distance between an minus 1 minus L. Now, this inequality is saying at every stage after capital N, the distance is getting smaller and smaller by mu. Am I correct? So this should give you some idea. Okay, this should actually converge to L. So let us try to see how does it work. So what do we have? You start with any. Exactly, 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 exactly. And this is precisely what we will do. As see, as long as first to do any mathematical question, it's very easier, like at this level of analysis to develop some basic intuition and which you correctly identify in this question. So once you have that, you can always think of writing a rigorous proof. So this is precisely what we will show here. Now mod n minus L is always less than this. And because we are starting with any, let n belongs to n is greater than n. We are starting with any natural number. Now again I can apply, right? It will be, now again you apply this inequality. So this will be an minus 2 minus L times mu square. Am I correct? Yes. This is correct. Now, you know, your n is here and your n is here. So we are going to n minus 1, we are going to n minus 2 until we reach this stage. Okay. So can I say that now an minus 2, again if we apply this inequality which is given in the question, it will less than equal to mu cube an minus 3 minus n. Am I correct? Now you keep on doing this. If we keep on doing this, we will reach an minus l. Yes or no? Because you see, this is getting smaller and smaller. The index is getting smaller and smaller. So eventually we will reach this capital N. Am I correct? Because capital N is the smallest. We are starting with some natural number which is greater than equal to n. So what power of mu should come here? No. Small n minus capital N. Am I correct? Okay. Now, is this a fixed number? You see, capital N is fixed, so A subscript N is fixed. Yes or no? Sorry. And cap O. Sorry, here this is not small L. This is. I'm sorry for the confusion. This is capital L. Yeah. Yeah. Now, what can you say about on the right hand side? This holds for all n greater than equal to n. Now you know since mu is between 0 and 1, what can we say about limit mu n minus n? Yes, n going to infinity and n greater than equal to n. This is 0, right? Yes or no? So, by sandwich theorem, what we have proved is that an minus l, it is always greater than equal to 0 because this is a modulus of some entity, and this is for all n greater than equal to n. Now this side goes to 0. Am I correct? So by sandwich theorem, what you should be able to conclude? The middle one also goes to 0. That is limit mod a n minus l is 0. Am I correct? But this is precisely saying that limit a n is l. So hence we have proved correct. This was not difficult, was it? So where we have used the fact that mu is between 0 and 1. We have used this fact, right? Where exactly. So this information was a crucial piece of information. Okay? Yeah. Okay. Now let me put some another question for you. Just a minute. So let f be a continuous function from a to b to r. Okay? Be a continuous function and let x1 x2 xn. You take some finitely many points between a comma b. Okay, maybe like, and again you take some g1 g2 gn. These are some real number, non-negative. Then show that f of xi I going from 1 to n is actually f of xi for some xi between a to b. You read out a question, then please ask question. First you read the question, then we will discuss. So this, what do you think? Which theorem gives you some conclusion like this? You know, there exists some xi such that certain equality holds. What do you think? Yeah, some roles, but roles involves derivative, right? Here you have no differentiability. So there is another theorem na, that we learned in the beginning. Exactly. So, but yes, exactly. So the hint is you need to apply location of roots theorem. Now to apply location of roots theorem, you need a certain function, right? So you have to construct some function out of this f on which you can apply location of root theorem. Okay, I'll give you some hint. You want some xi such that f of xi is equal to something of this sort, right? Yes or no? But this is under the assumption that this summation is non-zero. Let us for the time being assume that this summation is non-zero. So clearly you have a certain function which plays role here. Correct? Does this give you some function, some continuous function? If you assume that this g1 plus g2 plus gn is non-zero, yes, this is a continuous function, right? So let us see. Let us try to do it. Okay. See why we are doing these certain questions, because later on you will see when you will be learning your numerical analysis course. For example, this thing, the first question that we did. This is a crucial step in the proof of bisection method. Okay. Don't think that we are doing any random question just to learn the convergence. No, all these questions will appear in one form or another in the proof of the techniques that you will learn in bisection method. So I request all of you to be, like see through it and discuss if you have any doubt. Yeah. No, I'm not saying this is a bisection method. What I'm trying to say that this this inequality, whatever the first question was, you will see that this appears as the crucial step in the proof of bisection method. Okay. This will appear as a crucial step, as an important step in the proof of bisection method. Okay, because here this mu will be half in that bisection method. Okay, the mu will be half because the interval was getting chopped by half every time. Yes. So then you will remember this proof, and then you will be easily, recollecting the proof of bisection method. Now let us do this. So okay, you have been given that these GIs are non-negative for I equal to 1 to n, and let m be the maximum of f of x1, f of x2, blah 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 f of xn. I can always take the maximum, right? Because these are finite numbers. Yes or no? And let small m be the minimum. Now I am writing one inequality. You tell me whether it's true or not. Summation f of xi gi. Can anyone give me one upper bound for this? It will be less than equal to capital M times summation gi. Yes or no? Yes. And what will be the lower bound? Yes. Very good. Now let us call it 1. And we develop case 1 here. Case 1 when So there can be two cases when this summation gi is 0, right? Or it can be non-zero. So if it is 0, then this is case 1. So what happens if this summation gi is 0? Very good. Because each gi is positive, right? Each gi is 0 since every gi is greater than equal to 0 for each. Yeah, that's it. So then by 1, what do we have? Then summation f of xi gi is 0, and this inequality will hold, right, for every x? Yes or no? You choose any. Okay, let me just put xi here so that there is no confusion. Am I correct? See, you see the left hand side, this is always 0, right? Because each gi is 0. Now the right hand side is also 0. This summation is 0. So it doesn't matter what f of xi I am multiplying it with, this will always be 0. Yes? So, but this was the required equality. This is what we want, right? For some xi. So these two are equal in this case, right? You see, these two are equal. Huh? Sorry. So, is it understandable in this case? Is it clear up until now? Okay. So in this case, any xi you choose, it works. We want only one choice of xi, but in this case, any xi work. Now let us discuss case two. Yeah. So what will be the case two? That xi I is not equal to 0. So if it is not equal to 0, what does it mean? That this is strictly positive? Yes. And because each gi is greater than equal to 0, so the sum will always be greater than equal to 0, but it cannot be 0 by this case. So the sum has to be strictly positive. Am I correct? Yes. Now what can you say about 1? I can divide by this number, right? All three side, and equality will be same because this is a positive number. Am I right? So what I'm trying to say here, that 1 implies m is less than equal to summation f of xi gi 1 going from 1 to n upon summation gi 1 going to 1 to n, then less than capital. Am I correct? Hmm. Now, you know that this m was, this, what was m? M will be, m was minimum of this f of x1, f of x2, blah blah blah, right? So, m would be some, like there, can I write, there exists some alpha and beta in a comma b such that f of alpha will be small m and f of beta will be capital M. Am I correct? Because this is a finite number, like f of x1, f of x2, all these are finite number. So their maximum will come among from this only, right? This will be equal to some f of xj. Am I correct? Maximum of n members will come from this only, right? Because this is a finite set. Am I clear? Yeah. So similarly it goes with the minimum also. So what does it imply, the above inequality? That f of alpha is less than equal to f of beta. Yeah. Now what should we do? Can anyone tell me? Of course, this summation runs from I going from 1 to n. Okay, let us define a function. Let us define a function on this alpha beta. H of x is f of x minus summation f of xi gi by summation gi. Okay? Is this a continuous function? Because this is a scalar quantity, right? The middle one is a fixed number, and f is a continuous function. Now tell me, what is h of f? What is h alpha? Is it negative? And what is h of beta? Is it positive? So can you apply location of roots theorem? Now, what does location of roots theorem says? Please tell me, what does location of roots theorem says? There exists some xi between alpha to beta, correct? Such that h xi is 0. Am I correct? This is location of root. Yes or no? Now, h of xi is 0. You just put the value and what will you get? That f of xi is summation f of xi gi I going from 1 to n by summation I going from 1 to n gi. Correct? Yes or no? And this is what we had to prove. You just see the question once again. Okay? Have we proved what we wanted to? Yes. Okay, good. Now, is there any doubt up until now? Please ask. If there is any amount of doubt, then please ask. Okay, I get that. You are basically asking if given a question how to proceed, right? Okay, so that has a very standard answer because we are learning maths, right? So a good answer would be you practice questions. Whatever assignment that are there in your numerical analysis course, because we are learning numerical analysis, so you will see a lot of proofs in the beginning. Even at the end of this course you will see, for example, bisection method, Newton-Raphson method, and then secant method, and all of this will involve intricate proofs. When I say intricate proof, it basically means the proofs that uses your conceptual knowledge of real analysis. So if you follow those proofs, certain ideas will come into your mind that will motivate you to, like, start with a certain solution. Okay, just a minute, give me a minute. दीप इसका वो लो बैटरी आ गया, जल्दी कर, जल्दी चार्ज में लगा। ये है 9%। कहाँ गया जीमेल, कहाँ गया मेरा, मैंने वीडियो बंद कर रखी है, कहाँ गया, आ जा एक बार जल्दी। नहीं है इसका चार्जर, रूम पे पड़ा हुआ है। अरे कहाँ से जाएंगे, किसमें, मेरा जीमेल छूट गया। काटियो मत कुछ, ये मत काटियो। एम आई ऑडिबल? हाँ, okay, sorry, some misconnection was happening. Yes, okay. So what I was telling you, that you need to learn certain concepts from real analysis. That would be my main focus for you to tell, because only then you will be able to answer certain questions in numerical analysis. So try to do as many questions as possible. Okay, and see, whenever you see a proof, try to see what technique is developed there. And that is how you do proof. There is no set solution, or like, there is no fixed path. The questions that we discussed today, it can have some alternative solution, right? So you cannot say, like, if I proceed only this way and only particular way, only then I'll be able to get solution. So you just start from somewhere and see if it works or not. Maths is basically based on a very strong hunch, but that hunch is easily developed if you keep on practicing questions. Okay, so don't worry about like thinking whether I will be able to prove it or not. You just start the journey. That is it. Yes, any other question? Ananya, do you have any question? Okay, Anuj. Okay, okay, Shiba Joseph, I can see Shiba Joseph, Sri Hareen. I can see many people who are there. Please, if you have any question, I request you to ask. Or if you have any comment for that matter, like you are going too fast, or this thing was not clear. If you have any such comments are always welcome. Maybe in the next lecture, I'll be more careful. So if you have any comments, please tell me, because it is a long journey for all of us. We have just started. This is week one. We have 12 weeks to share with each other on this journey of numerical analysis. If you have any comment, please tell. Yes, yes, yes. I will be there for next Sunday and the coming Sunday from 3 to whenever we finish. Okay, we have been allotted a slot for 2 hours, and huh, 3 to 5. 3 to 5. But exact 3 to 5, we know it's not possible because sometimes we'll be finishing a bit early. So, but like, if you have doubt, then session is always useful. So let us try to make such sessions as useful as possible. And I think that is only possible if each one of us feels free to discuss. That would be my suggestion. And because again one thing, I'm also a learner here, so I might do some mistake, but again it's a learning process for all of us, for you as well and for me as well. So that is why I'm asking if you have any comment that I was going too fast or I was going too slow or this thing you should have done in a different way. Please tell me right now so that in the next lecture I'll keep all these things in mind. For week 1 lectures, you see the NPTEL videos. Okay, you must have those lectures, right? You have enrolled in the course, correct? This is related to the basics of numerical analysis because we have to start from somewhere, right? And yes, in the week 1 you will be learning bisection method and all these things where all the theorems from real analysis that we have discussed will be useful. See, I think my part or my aim is to discuss the real analysis part that goes behind numerical analysis. Do you get what I'm trying to say here? Because see, assignments we will not be discussing assignment because for that is for yours to solve, and we have yes, yes, yes. We do. Yes, yes. That will always be the most suitable thing for all of us to do, right? To discuss what is happening in a given week. It might so happen that we can go faster or mostly we'll be behind the week's lecture. But it's always, a good thing to discuss where we are at. So you see the NPTEL videos, it is always preferred you see NPTEL video and then we can discuss some questions from that week's lecture. Okay? Yes. Okay, so if you have no doubt, then we can finish this session. You may leave. Okay. See you next Sunday. Yes, yes, yes. Okay. Yes, thank you. Yes, yes. If you have no doubt, you can leave. Yes. जी जी Sriharin, you have any doubt? So, in today's lecture, we learned convergence of a sequence, continuous function. Then we saw some preliminaries and results, which is location of roots. We saw its geometrical interpretation. What does it mean for a function to satisfy location of roots theorem? Then we saw some examples. Example particularly discussing bisection theorem. Then we saw Rawls theorem, which is about the differentiability and the root of the derivative of a function whenever it exists. Then in the end, we discuss some question involving convergence of a sequence. दीप कहाँ से वो करना था? जल्दी आ, सेव कर दे।